Good morning, or good afternoon, or good evening, whichever the case may be. Recall that over the last few class sessions, we've been looking at the arithmetic principles of addition, multiplication, subtraction, and two kinds of division, partitive and quotative. Now we want to look at sessions on computational strategies where these arithmetic principles give rise to a single set called the target set, and we want to determine ways in which we can determine the size of this target set through computational strategies. In terms of a graphic illustration, this slide on finding the size of target sets, it says, recall that arithmetic principles or combinations thereof lead to a special set whose size we wish to determine. This special set is called the target set. For example, in addition, the collection of given sets with objects characterized by a common unit of measure are merged together to form a single set called the target set. We want to know its size. That is, how big is it? So the arithmetic principles or combinations of the arithmetic principles lead to a target set, and we want to find the size. In this first session, we're going to look at the arithmetic principle called addition. And so remember that these computational strategies all fall under the general umbrella term called compensation. And remember that compensation is nothing more than modifying any arithmetic expression in such a way so as to take advantage of friendly numbers, or single-digit arithmetic, or power 10 arithmetic, or perhaps all three of them. Let me illustrate that very briefly, what we mean by taking advantage of friendly numbers, single-digit arithmetic, and combinations thereof. So we're going to turn to a full screen, and I want to give an example of what it is that we were saying in terms of modifying arithmetic expressions so as to take advantage of friendly numbers, single-digit arithmetic, power 10 arithmetic, or combinations thereof. Look at this first simple example. And symbolically, what we've written down is that we have three groups of objects, all with the same common unit of measure. And in the first group, there are 7 objects. In the second group, there are 9 objects. In the third group, there are 12 objects. And we want to know that if we were to take those 3 groups and push all those objects together into a single set called the target set, what is its size? And we said that what we would like to do is, in arithmetic principle, how do we modify this? How do we change it? How do we rewrite it in such a way that we can take advantage of, say, friendly numbers? In this case right here, in addition, we know that numbers that end in 5 or end in 10, those are the friendly numbers. Those are the numbers that kids are able to work with very quickly. They can bounce off of these numbers, 5 or 10. So in this arithmetic expression, 7 plus 9 plus 12, and we want to find out what the size of the target set is, since they're comfortable with tens, what they might do is they take the 9 and they might shift 3 units over to the 7 and make it a 10. That takes 3 away from the 9, makes it a 6, and then we're down to 12. They may not like the 12. They may want to reduce it by 2 and shift 2 units over to the 6, keeping the 10. And so if they share, and the strategy is called sharing, and we'll look at it a little bit later when we get into arithmetic principle of addition and its computational strategies. This is called sharing. We will take the 12 and we'll push 2 down here and make this an 8. And this will be a 10 then. And now in this particular arithmetic expression, the kids feel very comfortable. They've got 2 10s to work with an 8. And so they'll quickly say that 10 and 10 is 20. Then 8. They'll want to know what that is. Then finally they'll say that 28 is the size of the target set. And that strategy is called sharing. And once again, it takes advantage of the idea of friendly numbers. 7, 9, 12, neither of those 3 numbers are friendly numbers. So what they did was take 7, modify it by adding 3 of the 9 to it to make a 10, and then remove 2 from the 12 to get it down to a 10 and share that with the 8. And we bring it down to a number that's easy to compute, 10 plus 8 plus 10. Here's another example. Let's take 2 rather large groups. First one has 643 objects in it. Second one has 879 objects in it. And we want to know if we took those two groups together and merged them into a single set called the target set, what is its size? Well, we said that compensation is a way to modify an arithmetic principle like this one here, modify an arithmetic expression rather, and modify it so that we take advantage of either friendly numbers, single-digit arithmetic, or power 10 arithmetic. And what we will do is take and decompose 643 into 600 plus 40 plus 3. And of course, that's a value expanded form for 643. We'll do the same thing for 879. 800 plus 70 plus 9. And by taking 643 and 879 and decomposing it in the standard place value decomposition, what I've accomplished is this. I don't have to find 643 objects added to 879 objects all at one time. I can do it in several steps by splitting it up, decomposing it into what we call friendly numbers. 600 and 800 are power 10 numbers. They're friendly numbers. 40, 70, they're friendly numbers. They're power 10 numbers. And the 3 and the 9 are single-digit numbers. That's the reason kids, by the time they reach second grade, they need to know their single-digit arithmetic, at least up through multiplication. So now I'm going to do what we've been teaching our kindergarten and first graders to do, which is always start with the larger numbers. So they're going to take the 600 and 800, and that means 6 100 8 100s, so that's 14 100s. Then they move over to the group of tens. So they have 4 tens or 40, 7 tens or 70, and when they add them together, that's 11 tens or 110. And finally, they'll go to the single-digit numbers. They'll add those together, and they'll add 9, 3. And they might even use sharing. Pull 1 from 3, add it to the 9, make it 10, so it's 10 plus 2, and they'll get 12. Now, that's the first step in taking advantage of friendly numbers, power 10 arithmetic, single-digit arithmetic. And we get to this point, now we want to write this number in standard form, so they'll notice that they'll have 1,000 over here from the 1400. Then they'll leave the 400 because they'll leave it in the 400s column. They'll take 100 from the 110 and move it over to here. That will leave 10 back on this one. Then they'll take 2, leave it there, and take 10 from the 12 and move it over into the tens column. Then they'll add these together. And so now they have 1,000 plus 500 plus 20, and finally plus 2. And then they'll write this in what we call standard form. So this will be 1,522. So here is an example, 643 plus 879. We want to take advantage of friendly numbers, power 10 arithmetic, and single-digit arithmetic in order to make the computations easier, facilitate the arithmetic. So we split it up into friendly numbers, 600 plus 40 plus 3, 800 plus 70 plus 9. And although 3 and 9 are not friendly numbers, they are single-digit numbers. Now, what we want to do is turn back to what it is we want to accomplish over these next few videos. So we are in the process of all of this. We're trying to help our teachers to help their kids learn to count and measure in increasingly faster, more efficient, more sophisticated ways. And so that's what we're trying to do. So over these next few videos, you're going to see these statements illustrated over and over again. And that is through the general progression of these arithmetic strategies or the computational strategies, you'll see them being applied to small size sets or numbers, and we're going to graduate to large size sets or large numbers. And again, the first arithmetic principle we're going to focus on is the arithmetic principle called addition. So recall, in the addition principle, you have two or more objects, two or more groups of objects, and they all have the same common unit of measure. And we want to find out if we were to take all these groups of objects, two or more, and merge them together into a single set, it will form the target set, and we want to count the objects in the target set. So in this first example, where we see 8 plus 5 plus 11 equals what, or what's the size of the target set, we have three groups of objects, 8 in the first, 5 in the second, 11 in the third, and in this picture, the unit of measure might be beach balls or just balls, colored balls, and we want to find out if they were to take these three groups and merge them into a single group called the target set, what's the size of this target set? Now remember, one of the first strategies is sequential counting. So by the time kids get to first grade, they are starting to become what we call good sequential counters. So in the principle of addition, in this next slide, you'll see I've got three examples at the top of the page. I've got two groups of objects, one with 7 and one with 11. I want to find out if I merge those two groups of objects into a single set, the target set, what is its size? In the second example, I've got three groups of objects, first one with 17, second one with 25, third one with 39. If I were to merge those three groups of objects into a single set, the target set, what is its size? And the third problem is the kind of problem we want our kids to get to. It's not just a prompt question. In that one, there are three groups of objects. I know how many objects are in one group. I do not know how many objects are in the second and third group, but I do know that the size of the target set's 25. Can I figure out what the sizes of the second and third groups are? So in this list provided here for strategies for finding the size of the target sets, you'll see the list start off with sequential counting. Then you'll see counting on combination pairs, any order property, subitizing, compatible pairs, mental math, value expanded form, place value expanded form, table array, and lattice array. We want to look at each one of these and make sure that we understand these. Now, these are progressive. These computational strategies are the ones that are used by kindergarten and first graders, and they move up to the kinds of strategies that third, fourth, and fifth graders will be used in finding the size of target sets that emerge from the principle of addition. So we just got through illustrating sequential counting, but let me go back to that slide. And in this slide, these three groups of objects were merged together into a single object. At the kindergarten and first grade level, we really want them to form the target set. We want them to fully understand the principle of addition. And so physically, with manipulatives, they're going to actually form the target set, and then they're going to determine the size of the target set by some sort of computational strategy. For them, the beginning strategy will be sequential counting, possibly skip counting. So they'll go through and they'll count those beach balls or those colored balls one at a time until they get to the final count, which would be 24 in this case. And so they'll know that if they add three groups together, the first with 8 objects, the second with 5 objects, the third with 11 objects, that if they merge them together, that the target set size, that is the number of beach balls or colored balls in that target set, they'll know is 24. Now, gradually, we want them to be able to count the size of the target set without forming the target set. So they'll look at the three and figure out, is there a way that I can count the beach balls or the colored balls just in the three groups without forming the target set? And we want them to get to that point. And they'll be able to do that. One of the first ones is if they just have two groups of objects, they may have a situation where, in the problem I just illustrated, they may have two groups of objects, could be 7 cookies in one box and 11 cookies in the other box. If they were to take those two groups of cookies and put them into a single box or put them all on a plate, we want to know how many cookies there are on the plate or what would happen if we merged them together. In kindergarten and first grade, they're taught to use the computational strategy called counting on. And they're always coached into starting with the larger number. So in this case, they're starting with 11. and then they may use their fingers, and I will illustrate that to you. They're starting off with 11, and they've got 7 objects they want to add to it. So they say 11, then they go 12, 13, 14, 15, 16, 17, 18. So they've added 7 on to the 11. They got 18 in the count, so they know that the size of the target set is 18. So they know there are 18 cookies on the plate or 18 cookies on that box, and that's called the counting on strategy. And we talked about that when we talked about the arithmetic principle called addition. So let's go back to our screen. So we know that we've gone through in our early list. We know what sequential counting is. We know how that strategy is used. We know what counting on is used, and counting on, of course, can be used with 3 sets. It doesn't have to be restricted to 2 sets, and they can use that strategy called counting on. And then we want them to begin to think about things called combination pairs. So let's look at what combination pairs are. Combination pairs are pairs of numbers that lead to what's called friendly numbers. Now, friendly numbers we've already talked about. Friendly numbers for addition are those numbers that in their ones place, they end with 5 or 10. Okay? So numbers like 5, 10, 15, 20, 50, 100, and so on, those are friendly numbers. Kids like to work with friendly numbers because they are taught in kindergarten, first grade, that those are good numbers to work with, and not only that, they see that those are good numbers to work with. So compatible, or not compatible pairs, but combination pairs of numbers, in addition, are those numbers whose sum, whose total, is a friendly number. So the first set looks like, what can we add together to get a 5? Well, those 4 plus 1 is 5, 3 plus 2 is 5, 5 plus 0 is 5. These are combination pairs, and we want to create a learning environment where the kids, through manipulatives and through abstract symbolism, such as what I just wrote down, they become so familiar with these that they know them, they learn them. We don't want them to memorize those things. We want them to learn their combination pairs, and we want them to learn their combination pairs for 10. So we want them to know that 9 plus 1 is 10, and we want them to know that 8 plus 2 is 10, and so on. So these are combination pairs. And combination pairs are pairs of numbers which, when added together, give rise to a friendly number. And it could be numbers like 8 and 7, because 8 plus 7 is 15, which is a friendly number. So 8 plus 7 is a combination pair. And we want them to learn their combination pairs. And while they're working with combination pairs, it's going to give rise to this idea of subitizing. And it's an educational term that simply means recognition counting. So subitizing is recognition counting. So subitizing is a fancy educational term that means when I look at it, I already know what the result is. I already know what the size of the target set is going to be. And so recognition counting is really, the kind of way we would explain it. But it means things like with combination pairs, when we see 7 plus 3, we know what the answer to that is without doing any kind of figuring out on our head or getting out a pencil and paper and doing some scribbling. We know that that's 10. It's a combination pair. We want them to see that 10 plus 10 is 20. They'll know that without doing any calculations. They know that's 20. So it's true for combination pairs. It's also going to subitizing is going to lead to other pairs that are not combination pairs, like 9 plus 3. And after they see the relationship between 9 and 3, they know immediately that's a 12, because they understand the relationship of 9 to another number. and that is that I could take 1 from the 3, make it a 10, and so it's really 10 plus 2. But they'll see that automatically and make that a 12. So subitizing just means they look at an addition pair. Could be an addition triple, in fact. 3 numbers written together with the addition symbol between them, and they know what the size of the target set is. They know what the sum of the total is without doing any calculation or any mental math. So in this list of computational strategies for addition, we've talked about sequential counting, which is just to go in and form the target set and count the number of objects in the target set. Counting on, which usually refers to finding the total number of objects in the target set if you just have 2 groups that you're merging together. And you always start with the larger of the 2 groups, or the larger number, and count on to the smaller group, a smaller size. We've talked about combination pairs. Those are pairs of numbers that add up to friendly numbers, those numbers that end in a 5 or a 10. And we talked about subitizing. So before we talked a little bit about compatible pairs, but I want to go back and talk about the any order property, which is an important property that holds for both addition and multiplication. So let's talk about the any order property. So let's go back to example. Let's get to our full screen. And so what we want to talk about is the any order property. Now, the any order property is one that emerges from this important idea that I mentioned in class and previous video sessions. It's Piaget's conservation of number. And recall that Piaget's conservation of number is the one that declares that if you have a group of objects, that if you rearrange those objects in any way whatsoever, it doesn't change the size of the set. And so the nice thing about addition, if I start off with 7 plus 9 plus 4 plus 3 plus 1, and I want to know if I have 5 groups of objects, 7 in the first, 9 in the second, 4 in the third, 3 in the fourth, and 1 in the fifth, and if I were to form the target set and merge those 5 groups of objects together, I want to find the size of that target set. What would it be? Well, the any order property is basically based on the physicalness of these. If I had 7 objects in this set and 9 objects in this set, 4 objects in this set, 3 objects in this set, and just 1 object in this 5th set, then no matter how I arrange those groups, I could put this group, I could put over here and slide it between the second and third group, and I could take the group of 3 objects and over here and slide it in between the first and second group. And remember, Piaget's conservation of number says no matter how I arrange or rearrange those groups of objects, I'm not going to change the size of the target set. So if I took all these 5 groups, even if I repositioned them and pushed those all down into a target set, one group, it's not going to change its size. But by making this change, notice what I've done. If I push the 3 with a 7, then it makes it so that I change this to 7 plus 3 by moving the 3 objects over with the 7 objects. And if I move the 1 over between the 9 and the 4, I'm really adding 9 objects to 1 object, or a group of size 9 to a group of size 1. And finally, I've got the 1 set 4 all by itself. So I put the 2 groups of objects, one with 7 and 1 and 1 with 3 together. I put the 2 groups, one with 9 and 1 with 1 together, and I left 4 by itself. But what this does, it makes it so that this is a combination, it's 10. This is a combination, it's 10. So I've got 2 groups of 10 finally added to 4. And of course, that quickly seemed to be 24. So the any order property for addition says I can move the numbers around in any way I want to in order to help me figure out what the size of the target set is. So whether you switch the the position of the 3 and the 1, which is called the commutative law, or I take the last 3 and I group 4 and 3 together, or group 3 and 1 together, which is called the associative law. I just think all of these can be blended together just to simply indicate that I have an any order property, which means I can take any set of numbers, rearrange the numbers, okay, and I'm still going to come out with a target set that has the same number of objects in it. And that's the any order property. And again, Piaget's conservation of number, as I've told you several times in class and in previous video sessions, it's the most powerful idea, I believe, the most powerful idea in all of mathematics, and certainly one that gives freedom to our kids when they do computations. So let's go back to our array or chart to make sure we've covered everything. So we've gone through sequential counting, counting on combination pairs. We've talked about the important any order property, subitizing, and compatible pairs are pairs that include combination pairs, and these are the things that this set of compatible pairs grows with age and grade level. And so their list of compatible pairs begins to increase through experience, and they start learning that 7 plus 7 is 14, and 9 plus 9 is 18, and 21 plus 3 is 24. Even those are not combination pairs, they understand because of their number fluency and their number sense. They know how to find the sums of things without actually having to do calculations. So they're subitizing. And so this brings us to mental math.